Albert Einstein's theory of general relativity, proposed in 1915, revolutionized our understanding of gravity. It portrayed gravity not as an invisible force, but as a curvature in the fabric of space-time caused by mass. Imagine space-time as a stretched rubber sheet, a heavy object like the sun. Dense this sheet, and planets follow the curves around it. This elegant theory explained the orbits of planets and even predicted new phenomena. One of these phenomena was gravitational waves, ripples in space-time itself. According to Einstein, accelerating massive objects like colliding black holes should send ripples through space-time. These ripples, or waves, were predicted to travel at the speed of light, distorting space and time as they passed. However, Einstein himself doubted if such waves could ever be detected. He believed they would be too weak to measure with any technology then imaginable. Despite his doubts, the idea of gravitational waves intrigued scientists. Over the decades, they sought ways to detect these elusive ripples. It would take nearly a century of technological advancement and innovative thinking before Einstein's prediction would be confirmed. The journey was long and fraught with challenges, but it was one that promised to unlock a new way of observing the universe. Initially, Einstein was optimistic about the existence of gravitational waves. His equations showed their presence as a natural consequence of his theory. However, his confidence in their detectability waned over time. By the 1930s, he began to express skepticism, doubting that any existing or foreseeable technology could measure these faint signals. Einstein's calculations suggested that the effects of gravitational waves on Earth would be minuscule. Einstein's skepticism was reinforced by the lack of direct evidence for such waves. Theoretical calculations alone could not justify the enormous effort required to build a detector. Moreover, the scientific community was divided on the issue. Some believed in the potential of detection, while others shared Einstein's doubts. This uncertainty slowed progress for decades. The skepticism was not merely pessimism, it was a reflection of the technological limitations of the time. Measuring the tiny distortions caused by gravitational waves required precision instruments that did not yet exist. It was a dream that seemed as distant as the stars themselves. Yet, some visionaries were undeterred, determined to turn Einstein's theoretical ripples into a detectable reality. The Laser Interferometer Gravitational Wave Observatory, or LIGO, was the brainchild of several persistent scientists. Among them were Rainer Weiss, Kip Thorne, and Ronald Drever. Each brought unique expertise and passion to the project. Weiss, a physicist from MIT, conceptualized a way to detect gravitational waves using laser interferometry, a method of measuring tiny changes in distance. Thorne, a theoretical physicist, contributed by refining the scientific framework and rallying support for the project. Meanwhile, Drever, a Scottish physicist, added his experimental skills, vital for tackling the practical challenges. Together, these three men laid the foundation for LIGO. They faced skepticism from both the scientific community and funding bodies, but their determination never wavered. Convincing the community and securing funding was a Herculean task. LIGO required an unprecedented scale of investment, both financially and in terms of human resources. The team's vision was bold: to build a detector so sensitive it could measure distortions thousands of times smaller than a proton. It was a gamble, but one with potentially groundbreaking rewards. Building LIGO was an engineering marvel. The observatory consists of two L-shaped arms, each 4 kilometers long. These arms needed to be perfectly straight and isolated from environmental noise, including seismic vibrations and even slight atmospheric changes. Achieving this required cutting-edge technology and innovative designs, pushing the boundaries of what was technically feasible at the time. The construction team faced numerous obstacles. They had to design advanced laser systems capable of maintaining stability over long distances. The mirrors used in LIGO's interferometers had to be polished to near perfection, with surfaces accurate to within a fraction of a wavelength of light. Even the slightest imperfection could disrupt the experiment. Moreover, LIGO's location had to be carefully chosen to minimize interference from human activity and natural phenomena. The construction spanned years, with meticulous attention to detail at every stage. It was a monumental task, but the potential payoff was immense. The first direct detection of gravitational waves, confirming Einstein's century-old prediction. Section 5. The breakthrough detection in 2015. On September 14, 2015, a faint chirp was detected by LIGO's sensors. This signal was the first direct evidence of gravitational waves. The source was a pair of black holes, each about 30 times the mass of the Sun, merging over 1 billion light-years away. As they spiraled together, they generated powerful ripples in space-time, which eventually reached Earth and were captured by LIGO. This discovery was a watershed moment in astrophysics. It confirmed a key prediction of Einstein's theory of general relativity and opened a new era in astronomy. The detection was not just about observing a cosmic event, it was about proving that the universe could be studied in a fundamentally new way. Gravitational waves offered a fresh perspective, allowing scientists to observe phenomena invisible to traditional telescopes. The announcement of this detection made headlines worldwide. It was celebrated as a triumph of human curiosity and perseverance. The detection not only validated years of hard work by the LIGO team, but also set the stage for future discoveries. The universe, it seemed, was talking in a language we had finally learned to hear. Section 6. Beyond a single wave, multi-messenger astronomy. The discovery of gravitational waves marked the birth of multi-messenger astronomy. This approach combines different types of observational data, like gravitational waves and electromagnetic signals, to provide a more complete picture of cosmic events. A landmark event in this field occurred in 2017, when LIGO detected waves from a neutron star collision. This event also emitted light and other signals observed by telescopes around the world. This multi-messenger observation was a scientific goldmine. It confirmed that such collisions are a source of heavy elements like gold and platinum. It also provided insights into the behavior of matter at extreme densities. The ability to observe the same event through multiple messengers dramatically expanded our understanding of the universe. Multi-messenger astronomy is transforming our view of the cosmos. By combining data from different sources, researchers can test theories more rigorously and uncover phenomena that might otherwise remain hidden. It's a powerful tool that promises to deepen our understanding of the fundamental forces and particles that govern the universe. Section 7. The future LISA and dark matter mapping. The success of LIGO has paved the way for future projects like the Laser Interferometer Space Antenna, or LISA. LISA is a proposed space-based observatory designed to detect gravitational waves from even larger and more distant cosmic events. Positioned millions of kilometers apart, its detectors will offer unprecedented sensitivity, opening a new frontier in gravitational wave astronomy. One of LISA's exciting prospects is mapping dark matter. While dark matter doesn't emit light, its gravitational effects can be detected through the subtle distortions it causes in space-time. By observing these distortions, LISA could help map the distribution of dark matter across the universe, shedding light on one of the most elusive components of the cosmos. The potential discoveries from LISA and other future projects are vast. They promise to unravel mysteries about the early universe, the nature of black holes, and the fundamental laws of physics. As our tools become more sophisticated, so too does our capacity to explore the universe's hidden depths. Section 8. Broader implications for physics. The confirmation of gravitational waves has profound implications for physics. It not only validates Einstein's general relativity, but also enhances our understanding of the universe's behavior. Gravitational waves offer a new way to test the limits of known physics, potentially revealing discrepancies that could point to new theories. This capability is crucial as scientists seek to unify general relativity with quantum mechanics. The two pillars of modern physics, they currently describe different aspects of reality and are yet to be reconciled into a single framework. Gravitational waves could provide the clues needed to bridge this gap, offering insights into the quantum properties of gravity. Beyond theoretical implications, gravitational wave astronomy is revolutionizing our understanding of cosmic events. It allows us to explore the universe's most violent processes like black hole mergers and neutron star collisions in unprecedented detail. This new perspective is reshaping our understanding of how the cosmos evolves and behaves. Section 9. Concluding thoughts on the cosmic symphony. The detection of gravitational waves is one of the most significant achievements in modern science. It confirms a century-old prediction and opens a new chapter in our exploration of the universe. By listening to the cosmic symphony of gravitational waves, we gain a deeper, more nuanced understanding of the universe's structure and history. This achievement highlights the power of human curiosity and ingenuity. It demonstrates how perseverance and collaboration can overcome even the most daunting challenges. As we continue to explore the universe through gravitational wave astronomy, we stand on the brink of discoveries that could redefine our place in the cosmos. The journey from Einstein's theoretical ripples to the first detected chirps has been long and arduous, but it is far from over. With future projects and technologies, we are poised to uncover even more of the universe's secrets, further enriching our understanding of the cosmic symphony that surrounds us.